Okay, oxidation states. An oxidation state refers to the charge of an atom, and even in the case of covalent compounds, atoms are still treated as ions, where the electrons shared between atoms with different electronegativity. So when that's happening, the electrons are given to the atom with the higher electronegativity. When atoms are shared between elements with the same electronegativity, they split the electrons. So what does that mean? Well, if we go and look at some compound, let's look at, I don't know what, magnesium chloride. Well, this is really made up of magnesium 2+ ions and chlorine minus ions, 2 of them. So the oxidation state of magnesium is 2+ and chlorine is 1-. I think that's easy for an ionic compound, but where this gets tricky is when we try to deal with covalent compounds. So let's look at something like NH3. To figure out the oxidation states here, we have to consider a couple things about the atoms. We have to consider their effective nuclear charge. What that means then is for an atom like nitrogen, who has 7 protons, we don't really care, but he's 7 neutrons, 2 inner electrons, and unbonded 5 electrons on the outside. We reduce this atom, when we're trying to understand its chemical nature, into a simpler atom. We say that all the inner electrons and inner protons act as one substance, and we give that substance an overall charge. That charge, in this case, becomes +5. +7 minus 2 inner electrons, giving us our +5. And then that tells us how this atom will behave chemically when reacting with other elements. So nitrogen in this case has an effective nuclear charge of +5. Now to determine its oxidation state in this compound using that effective nuclear charge, we also need to consider how many electrons nitrogen can sort of claim as its own. First of all, it can clearly claim this lone pair of electrons as its own. But also, to determine who gets credit for these shared electrons, instead of saying it's a covalent bond and so they're shared, for the perspective of oxidation states, we look at the electronegativities of the two atoms involved. The electronegativity for nitrogen is 3.0, and the electronegativity for hydrogen is 2.1. And we say whoever has the higher electronegativity gets to completely claim those shared electrons. So nitrogen would get to claim those ones, and those ones, and those ones, since it has the higher electronegativity in all of those cases. 2, 4, 6, 8. That means that it has 8 electrons that it gets to lay claim to. That means for our nitrogen, its oxidation state will be -3. And for the purposes of this electrochemistry, we're going to treat it as if it's a -3 ion. Alternatively, hydrogen, with its 1 proton, now has credit for none of its electrons, so it has an oxidation state of +1. And so that is how we determine the oxidation states in covalent compounds. Given all of this, now I'm going to run through some basic rules of oxidation states that we can use so that every time we want to know an oxidation state, we do not need to go through drawing the Lewis structure, but instead, for the vast majority of cases, we can simply look at the compound and calculate the oxidation state. First of all, elements. Elements either exist, like iron, in a metallic bond with no real covalent or ionic bonding between them, so iron solid. In which case, if iron is not bonded with anybody else, he hasn't shared electrons with anyone else, and so his charge remains as 0. Alternatively, a compound like oxygen can form a diatomic element, where it's sharing electrons only with another kind of atom that's the same kind of atom as itself. What that means is any electrons that are contributed to bonds will be shared evenly between the two atoms. In this case, since they're not gaining or losing electrons but sharing them equally, their oxidation state also stays at 0. And so the simple rule, the oxidation state for all elements is 0. Next, metals. When metals form compounds, they tend to form ionic bonds. Even if they don't form an ionic bond, they tend to have the lower electronegativity of the two atoms in the molecule. As a result, we always assume that any electrons that are involved in bonding for metals are lost by the metals. So their oxidation states are simply the ionic charge that they get for losing those electrons. For example, if lithium gives its electron to an oxygen atom, it ends up being lithium plus 1. And so its oxidation state for all the alkali metals who react by giving away one electron is plus 1. Similarly, for something like magnesium, an earth alkaline metal, when it reacts with a compound like oxygen, it reacts by giving away its 2 electrons. When it does that, its resulting charge is plus 2. So we know automatically all the oxidation states for every earth alkali metal are simply plus 2. For the transition metals, we know that they can act by giving away different numbers of electrons in different situations. So we have to look at the valence and look at the compound to determine what the charge on that metal is in that compound. We need to be careful here because we can have some tricky cases, something like lead carbonate, for example, where if we look at this without putting much thought into it, we might think that that lead has a charge of 2 plus by reversing our crossover. But if we recall, the charge on carbonate is 2 minus, so the total negative ion in this situation is 4 minus. So this lead is at a state of 4 plus. And so the oxidation state for lead in this situation would be plus 4. So if we have transition metals, we have to look at the compound carefully, determine what the charge of that metal is in that compound, and that becomes the oxidation state. Nonmetals are a little trickier. Some nonmetals, like especially the nonmetals near the staircase, carbon, phosphorus, sulfur especially, can have oxidation states that are very tricky to predict, and you have to basically either draw the compound out or hope that you can come up with the oxidation state of everything else that's in that compound. Carbon especially can take on a large number of possible oxidation states. Other nonmetals are not so hard to deal with. Halogens, like chlorine, when it reacts with something, say, like carbon, tends to have the higher electronegatividity. It's a halogen, it's on the far right, that's where the electronegativities are high. So in almost all of his cases, chlorine has the higher electronegativity. What that means then is any shared electrons get given to the chlorine. Typically this means that chlorine ends up with 1 more electron than it started with because it took the 1 electron from the shared pair. And so the typical oxidation state of halogens is -1. Oxygen is also a very electronegative atom, and so tends to take 2 electrons when bonding with other materials. So if we have something like, I don't know, I did carbon dioxide in the last video. Oh, well, let's say magnesium oxide. The oxygen will have stolen 2 electrons from the magnesium because he's stronger than almost all elements on the periodic table, and he has 2 spots to fill. What that means then is that oxygen will typically be at 2 higher electrons than usual, or an oxidation state of -2. If we can get the oxidation state of most of the atoms in a compound, and we're only missing one, then we don't need to draw out the Lewis structure to consider what the oxidation state is by considering the actual sharing of electrons. We can instead just look at the total of the oxidation numbers in a compound. The total of the oxidation numbers in a compound should always add to 0. Unless the compound is a polyatomic ion, which has a charge, and then the charge of the ion becomes the total of the oxidation states. So let's look at an example here. Carbonate, CO3 2-. We know that this has to total to a charge of 2-. We have one carbon, whose oxidation state we're not going to know, and we have 3 oxygens at -2 each. So this carbon would have an oxidation state of +4. So by knowing what the total oxidation is going to be, we can go back and find the oxidation states of atoms that might be trickier in the compound. This will work in most cases. Or there are some large organic compounds or complicated organic compounds where you still need to take the time to draw the Lewis structure to come up with what the exact oxidation states are for those atoms. But what I want to do now is I want to split some practice here, where in the next video I'm going to look at finding the oxidation states of a whole bunch of things using the numerical tricks we've just given here and not drawing out the compounds. And then I'll do a secondary video where I deal with having to draw out the compounds to find the oxidation states because they aren't as simple as using the formula.